David Smith here with one more Flipped Classroom math lesson video. 3 tips before we start. First, you can speed up or slow down the playback speed if that helps you get through the video. Second, you can pause the video at any time to catch up with your notes. Third, you can turn on the captions and watch my words go by on the bottom of your screen. Today's video is a further exploration of first derivatives and turning points for function graphs. So a quick review from our last lesson. The first derivative, f prime, tells us about whether functions are increasing or decreasing or whether we have a turning point. And remember, when you take an x value and you plug it into the derivative function, the f prime, it gives you the slope of the tangent line at that point on the function's graph. So here's the review. F prime of x, when that's less than 0, when that's negative, the function is decreasing, the graph is decreasing because the tangent line slope is negative, so that means the function is going down at that value of x. When the f prime of x is 0, that means the tangent line has no slope, it's horizontal. So that means we're at a turning point on the graph. It's changing direction from increasing to decreasing or vice versa. So that's where we have a turning point. So when f prime of x is 0, we have a turning point because the tangent line has a 0 slope. And then finally, when f prime of x is greater than 0, that is positive, that means the slope of the tangent line is also positive, and that means that the function's graph is increasing at x. In this lesson, we are going to consider 4 types of turning points: global minimum, local minimum, global maximum, and a local maximum. Now, I want to use a graph to show you what these mean. So we're going to take a look at the locals first. Local minimum and a local maximum. So in our graph, these are points A and B on the graph. So let's step over there and take a peek. So this is a local minimum. Right here, that's as low as the graph gets. That's as negative as y gets on this cubic function. Now, it's not a global minimum because the graph, after it goes back up, passes through that turning point, that goes down forever. So the graph as I've drawn it there has no global minimum. And likewise with this local maximum, again, it's a maximum right here at this turning point. But for the whole graph that I've drawn, there is no global maximum because y goes up, 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 up forever that way. So now I'm going to change this graph to show you a global max and a global min. Okay, so what I've done is I've restricted the domain. Now let's take a look at the graph first. Check it out. No more arrows at the endpoints. I've restricted the values of x that this function can have. And so that's this statement here. The domain is a set of all x such that x is greater than negative a and less than a here. So now that gives us a global maximum at C and a global minimum at D. By global, it means for the function as a whole, what's the max or what's the min? So I added these here, global minimum at D, global maximum at C. So this is a little contrived in that this function doesn't have a global maximum unless you restrict the domain. So when you do the problems in this set, make sure you pay attention to the instructions on the domain. All right, let's wrap this up with one more example to kind of bring it all home in a quick problem. So here's our function, 1/3 x cubed minus x squared minus 8x plus 3. First prompt, find and classify the turning points. So please, I urge you, be bold, pause the video, and complete this prompt before you come back and see how I did it. Okay, I carried this all the way through to the end. Lots of math on the board. So let's go through this step by step. Hopefully you gave it a shot and you got somewhere. Maybe even you got it 100%. So that's my hope. Okay, so check this out. The first thing we had to do is find the derivative of this function. So I used my power rule on the 4 terms there, and here's my derivative function. So I got that. Now what I need to do is set that equal to 0 and solve for x. That's going to give me my turning points because that's going to show me where the tangent lines have a 0 slope. So this factors down nicely, equals 0, and I get my 2 points at x equals 4 and x equals minus 2. So then what I did is I made my number line, I put my minus 2, I always put 0 on, and I put my 4. These are my turning points. I just now need to figure out where the function is increasing and where it is decreasing. So to do that, I did f prime of -3, which is a little bit further to the left of our turning point right there. I plugged -3 into my derivative function there. I did my math, I get +7, so I know the function is increasing all the way on its way to x equals minus 2. Then I plugged in 0 to test this interval between -2 and 4. I always pick the easiest values to test. So I did f of 0, and that one's really simple because I know these two terms go to 0. So there at 0, f prime is -8, which is negative. So I know the function is decreasing there. Finally, I tested a value to the right of my other turning point, which was 4. So I just put in 5, pretty straightforward. I did my math on that with my derivative function, and I get 7, which is positive. So there, the function is increasing. So I sketched my little curvy line here to kind of show the sense of the function on my number line. So I know I have a cubic function, most likely, or definitely, this is going to be a local maximum, and this is going to be a local minimum. Notice we did not specify the range, so we have no global max or global min. Now finally, like if that was the prompt, was classify the turning points, you're done. But I went ahead and found the points, I found the coordinates for those turning points, and it was kind of a pain in the butt because this function here has fractions in it, so I had to deal with fractions, I had to convert my answers in fractions, but I went ahead and did it. So the maximum, it occurs when x is 2. So I have to plug 2 into the original function. Notice it's not f prime, this is just f of x. So I plugged in my 2 in my cubic function here. There's my plug-in step. Here is my next step with one fraction and regular numbers. And then I had to convert them all to fractions, all to thirds, add them all up, and I get 37 thirds for my y coordinate. So that point is -2, 37 over 3. So that's my local max. My local min, again, same thing. I'm plugging my 4 into my original cubic function. There's my plug-in step there. I went ahead and did my math, and I got a fraction here. I went ahead and converted everything to fractions as I went, combine them together, and I get -71 over 3. So there is my local min, and it's the point 4, -71 over 3. All right, so now we're going to use the first derivative in a different way. We've got this rational function here, x minus 5 over x. So the prompt is use the first derivative to show that this function has no turning points. So before we jump into that, think about what that has to mean. We're going to take the first derivative, and then we use that to find turning points. So what do we do when we search for turning points? We try to find where the first derivative is equal to 0. So go ahead and do that and see if you can figure out how to show that this function has no turning points. All right, in case you were struggling to figure out how to differentiate this, I'm going to remind you of the quotient rule. We have a quotient here. We have x minus 5 divided by x. So we have a quotient rule. So the way to do that first is to break this down into component functions. So I had my u is my x minus 5. That's on the top of the fraction. And then my v is x. That's on my bottom of my fraction. Then I need to derivate each of these individual functions to get u prime and v prime, which both equal 1. So now pull out your quotient rule for derivatives and derivate this function. Here's my quotient rule using my u's and my v's and my u primes and my v primes. So that's just a restatement of the quotient rule. I went ahead and plugged in my values from this section here, and then I simplified on down, and I get 5 over x squared. So that's the derivative of x minus 5 over x. That's our y prime right there. So now we're going to move on. Remember the prompt. use the first derivative, which is what we just found there, to show why this function has no turning points. So take a look at that. Figure out why it has no turning points and come back. So check this out. 5 over x squared equal to 0. Solve for x. The truth is, there is no solution to that equation. If you put in 0 for x, you have an undefined problem because you have a divide by 0 problem. You start experimenting around, you're going to find that no matter what you put in for x, you're going to have some positive number on the bottom of this fraction, which means when you divide it into 5, you're going to have some positive number. So this function is always increasing. This is the derivative. So the function, remember, it gives you the slope of the tangent line. So no matter what you put in here, you're going to get a tangent line that increases, except you can't put 0 in. So pause the video and state the intervals upon which this function is increasing or decreasing. So here it is in our notation. It's increasing from negative infinity to 0 combined with from 0 to positive infinity. Notice the curvy brackets. That means it does not include 0. This function is undefined at 0. So now what we're going to do is we're going to sketch the graph of this function. Okay, this is a rational function. And if you recall from our section and our work there, rational functions have two curves that are defined by their asymptotes. And so this one, the thing you need to remember is that the vertical asymptote happens when the bottom is 0. And so that means that since there's only an x, when x is 0, we have a vertical asymptote. That's why these two curves are approaching the y-axis. That's when x is 0. And then the horizontal asymptote occurs when the coefficient of x, which in this case is 1, is added to whatever constant is out there, which in this case is 0. So the horizontal asymptote on this one is just 1. So I sketched that in there and I drew my curves. Now, check this out. This function is the derivative of this function is always positive. It means the function is always increasing. So you can see here that this function is always increasing. Tangent lines to this slope are always going to be positive, and the same with this one. The function is always going to be increasing. So we learned that. And then check it out. There's no turning points. There's no local maxima or local minima or global maxima or global minima. This function just goes up forever, positive in the y direction, goes negative in the y direction forever, it goes positive in the x direction forever, and negative in the x direction forever. So it's increasing everywhere except at x equals 0, at the vertical asymptote. There, the function is undefined. We cannot graph the function, we cannot talk about the function because we have a divide by 0 problem. Wait a minute, where's the outro? What happened? Thanks for watching. Just before you go, make sure to write down any questions that you have so that you can bring them to our next class and get them answered. Also, remember that you can watch the video again if you want to deepen your understanding. Finally, if you enjoyed the video, please click like or subscribe. Wow, something's going wrong here.